Okay, then let me introduce our next speaker. Our next speaker is Henning Lategahn, and he's currently Director of Engineering of 3D Maps for Automated Driving at Bosch. And beforehand, he was the founder and CEO of Lategahn, which is a company focusing on the development of 3D mapping technologies for autonomous driving. And in 2022, Lategahn was recently acquired by Bosch. Henning's background is in computer science, and he obtained his PhD in 2013 from Karlsruhe Institute of Technology, where he was mainly conducting research on mapping and localization for autonomous driving. We are very much looking forward to his talk. Henning is joining us over Zoom.
Okay, thank you very much. Let me get the slideshow started here. So please complain if you do not see my screen, as otherwise I assume you do see this. Yeah, thanks for the kind introduction, and also thank you very much for giving me the opportunity to talk to you guys here. I started in academia somewhere around 2009-ish, it's well over a decade ago. And then, went for the PhD, and obviously also went to scientific conferences to present some of the work I did. And then after my, let's say, academic work, I moved on and moved more towards the industry side, and haven't spoken at any truly scientific conference ever since. And now I'm being invited to talk to you guys here at the workshop, so I'm pretty excited about this. And I'm also hoping that stuff I would present here today will not be, too boring for you guys, because in some parts I can simply only, scratch on the surface and don't do the typical deep dive that you would otherwise probably expect. Yeah, like I said before, I'm the founder of Atlatech. It's a 3D mapping company, and it's just recently been acquired by Robert Bosch. And today I speak as a Bosch guy to you guys, right? But most of the work I'm talking about kind of originates back in the startup times when we started to build the 3D mapping technologies for automated driving. Okay, let me start with a very high level. Why do we do all this kind of things? In the automated driving space, we focus heavily on the level 4 autonomous driving, meaning driverless vehicles, and that also has some implications for the maps that lie underneath it to drive these autonomous vehicles. And you can see a snapshot here from a map we did a while back in San Francisco, so just a couple of blocks in San Francisco in the financial district. We thought it is a nice training field, because from GPS perception and a few other things, it's not the easiest. It's also not the most advanced, but it's also not the easiest thing to do. So we did a bit of mapping work over there. This is just a screenshot to give you kind of a gut feeling for what I'm talking about when I talk about 3D maps. But my key message here is basically our 3D maps consists of 3 different components, and these 3 different components is basically what makes the autonomous vehicle drive in these areas. For one, it's obvious, it's geometry, right? So when we talk about poles, then it's a question, where is that pole? I mean, where's the tip? Where's the bottom part of that one? How big is it? Where exactly is it? At what geographic location is it? Likewise for lane geometry, right? Obviously, the question is, where is the lane boundary to the left? Where's the lane boundary to the right? And stuff like this, like you can see on this picture here. And all of this I would, summarize as geometry, basically. Where is stuff, what's the shape of it, and where does it actually locate, right? That's one thing. Second is, that kind of sits on top of this, and that's attributes, right? I mean, geometry alone is not really meaningful in many cases, but what's missing, and it's important, is attributes. So if you have the lane delimiter as an example, let's take that one again, it's an easy one. We can also build the information of what type of lane delimiter that is into that geometry. So for example, is it a dashed, is it solid line, is it a dashed line, is it double dashed, etc. But in fact, it actually goes a bit further than that, because what's really important is what does that imply for any vehicle, be it autonomous or be it regularly driven, right? The question is any vehicle allowed by rules to actually pass that lane delimiter in this example or not? And if so, in what direction? Sometimes you can only cross left to right, but not vice versa. All that kind of information is, summarized in attributes and kind of attached to the geometry that we map. That's the second part. And finally, the third part is, it's also may or may not be obvious, it's relationships between these objects, right? So we can take the left and right lane boundaries and kind of combine these to form a lane. That's what we drive on. And then we can map out a, let's say, traffic light, right? And then we can also put the information of that very specific traffic light is associated with that very lane that we drive on also into the map. So that's all about relationships, right? And these are the three main pillars which we always map and put into these 3D maps, which then allow any, let's say, intelligent vehicle / autonomous vehicle to use that information to perform some driving tasks in an automated fashion. Okay. Why would anyone care in the first place? I think that's also pretty clear by now. We can treat, in this domain at least, we can treat our 3D maps that we build as a very strong sensor, right? It has some pros and it also has some cons, obviously, right? But the pro on the pro side is we can really map out all the non-moving objects with high precision, high completeness. We can even do manual quality control checks and all these kind of things to really try to get to a level that I would call, automotive level that you need. It's not only about kind of getting all the geometry, getting all the attributes. It's also a lot about what are the KPIs, how can you prove that you actually do meet these KPIs, etc., etc., etc. Right? We can do all of this, and then finally we have all these static objects in the map, and that's a big plus, right? Secondly, it has, let's say, a sensing range or field of view. This is almost arbitrary, right? I mean, you can also read data from the 3D map that's a mile ahead, right? Or even 2 or 10 or 100 miles ahead. Maybe it's not relevant, but you could in principle do that, right? So that's like almost infinite and unlimited sensing range and field of view, which is good, and high completeness, high accuracy, all these things I mentioned before. So that's strong on the plus side, right? On the minus side and on the con side is you can never really be sure whether it's up to date or not. I mean, this is the biggest drawback of any map-based approach that you see, right? I mean, is it still up to date, right? And from a pure mapping perspective, I mean, there's nothing we can do about this, right? I mean, back in the days when I was driving our vehicles to record data, I was in Detroit, I believe, right? And actually, I was on a highway to record data for a client, and I was a number of years back, right? And I was kind of driving behind a car that's repainting the road, right? So I knew while I was driving that it will be out of date once I pass that car, right? I mean, you can never be sure that anything like that happens, right? And that's like the biggest downside of maps. And there are other things that could be done to kind of keep these up to date, right? But on a very high level, this is a 3D map. That's why it's important, okay? Okay, to give you more examples of what that actually looks like, this is an example from Tokyo. There was, or still is, a pretty high interest in these kind of activities in Japan. First time I'm using PowerPoint in 20 years, and maybe I should learn a little bit, but the video is a bit bumpy here, not sure why. Sorry about that. Yeah, let me pause here for a second. So here you can see these typical objects that we scan and that we extract from our sensor data. I will explain in a second of how we do this, and that's basically the map that can then drive, any vehicle in these areas. Okay. And there are some details in there. For example, if you have these curbstones, whether it's an elevated or it's a lowered curbstone, all that kind of information we can put into these maps. I fast forward a little bit. And also looking at these maps from the video perspective allows one to do some elementary, let's say, quality checks, right? I mean, you can check to what extent, do these maps actually meet reality, at least at the time of recording the data, and how accurately does it fit, right? I mean, you can already pick out some of the things from these videos. Looking at these videos, there is one misconception that sometimes comes up. It's not that we take video data and label that data. We are not a labeling company. But what we are is we build technology to actually scan the world, right? And after we are finished with scanning and data processing and all the things we do, we have an exact copy of the environment like this one here. So this is the map that you see, right? It's nice to kind of look at that data from the camera perspective, but it has nothing to do with the camera, right? Or it has little to do with the camera. It's really that we have 3D geometry, and that is what the 3D map is, and that's what you actually can see in this video here, okay? Okay, so how do we do this? I think this is a much more interesting question to answer, right? And I will walk through a couple things here, and yeah, maybe we can also open up for questions at the end. Let's see what else we can talk about then at that part. But for now, we'll kind of walk through the stack, or at least kind of pick out a few highlights of what we do here and how we do things. And then again, I'm open to answering a couple questions at the end if we have the time. First things I want to mention is that we built the entire mapping stack, right? So when one starts out with 3D mapping activities, it's pretty obvious that eventually and at one point you need a point cloud maybe, or maybe you need some AI to pick out, lane geometry or road signs or whatever it is. And that is all true. I mean, that is needed. But to really build these maps for paying customers that use that map for autonomous vehicles, it takes a lot more than that, right? I mean, these super obvious things, it's really, over time, it's only becoming a small portion of the entire thing. And what we did is we built everything that's needed to actually do this. So we started with fleet management. How can we optimize the routes to record the data, How can we make sure that a very, let's say, cost-effective driver can actually use our stuff, right? So we do not expect an engineer to sit in the car, just a guy that can actually drive the car, that's it. Right, in a number of different locations, even as a small team, that's possible, right? We built our own sensor, we looked into self-calibration and a number more things. Then data processing of how can we, consume the data that we record and make it 3D-ish raw data. That's one thing. And then based on that, how can we extract everything that's relevant, topology, relationships, attributes, geometry, all the things I mentioned before. These are these two big blocks here. And then finally, how can we do this at scale? I mean, how can we march through a lot of data, and how can we make sure quality is high? How can we get the human in the loop? How can we make sure nothing is forgotten? How can we set up our processes to get kind of sign-offs during quality gates and all that kind of stuff that's needed? In the end, we are in automotive, right? And automotive is automotive, which means, I mean, reliability is a thing, and it's not that you can only do it on a small tiny intersection and then you have a mapping product. That's not how it works, right? I mean, there's a lot more to do, and I think we covered many of these aspects to actually build these maps. Okay, let's start with a sensor. It doesn't win a beauty contest, I think, but it's fine. I mean, it's made to be ruggedized and kind of do the job, and we are more on the software side than on the hardware side, and I guess you can tell from the image. But this is the sensor part. We developed this ourselves. It's heavily computer vision based, so the main sensor for most of the company history of Atlatech, we used 2 cameras and GPS alone to build maps. Now it's also in IMU, and LiDAR is optional, but it's kind of the recent things we added to the lineup. But it's really heavily based on computer vision, and this is also some things I want to talk about. I think it fits this workshop and it fits this audience, right? So, in a nutshell, it's a stereo vision system that's needed. Everything that's needed is in the box. I mean, mass storage, all that stuff is in the box, right? And it's lightweight, it's easy to build, it's easy to maintain, it's ruggedized, it's easy to ship, it's easy to mount, right? Setup time on a vehicle, that's even a rental car, it takes 10 minutes. And that's if you work slowly and do it the first time, right? I mean, our drivers that do it over and over again, they do that in no time, right? I mean, you can't even look that fast as quickly as they put that stuff on the car, right? And then you can basically drive with any car that's available, record the data inside that box, and after the data recording, it's uploaded to our servers. It's massive amounts of data, obviously, right? And then it's kind of where the magic happens. But the recording part is very easy, very lightweight. We don't need any calibration equipment. We do not need any checkerboards. We do not need any calibration targets. We do not need any tachymeters or whatever you typically use to kind of cross-calibrate with the vehicle, because that's irrelevant. It's not needed, right? Yeah, that's kind of the prototype of the latest version of it, latest generation of it. Here you can see that we can also use a LiDAR scanner. I mean, are there any questions? No, okay. So when we started out, I mean, these LiDAR scanners were prohibitively expensive. I mean, they were in the range of 70K or something, right? Euros/dollars. And nowadays you can get them for like some 10, 12, 15, 20K, right? Which is still, it still adds to the bill of material, obviously, but we are kind of at the stage now where in some cases it may make sense to actually use one. And I mean, we can build maps and we can build everything that's needed with 2 cameras. But we can also be honest that some things are simply easier with a LiDAR, right? And then why not use it, right? I mean, as long as it does the job, why not? Okay, let's move to fleet optimization. Again, this is nothing that one would think of as a first thing to do, clearly when one gets into the space, but it is something that is needed, right? And that's route optimization, right? So if you have a small area and you want to build a map of that area for, let's say, a customer or something, then we need to plan the trip, and we build software to actually do that in an efficient manner. And when we're talking about traveling salesman problem here, how do you can you traverse the network in the least amount of time or in the least amount of mileage to cover everything that's needed? And I can also say here that we drive on each lane once, at least once, right? Typically it's once, and that kind of even adds a little bit of complexity of, you know, how do you manage a trip, right? And this is really nice because it's a tool we build, and it can then kind of be driven and run by our project managers that actually look into these projects, and they can prepare each trip for each driver, for each vehicle, kind of do that in Karlsruhe in the offices. We are based in Germany, in Karlsruhe here, southwest Germany, and then kind of upload this to the cloud, to our Lategahn Bosch cloud, let's say. And from there, it is then automatically transferred to the drivers, and they get the routing information, turn-by-turn navigation, on their devices, which sits in the car. So this is another piece of software that we built here, which is a turn-by-turn navigation device. I mean, this is obviously from a test drive. I just realized that because Heid in Neustraße, that's where we are located as our office, somewhere down here. But this is kind of what it looks like, and here you can already see some statistics of what lanes have already been recorded, which other lanes are still due and need to be recorded. And one thing that's important to us is that this tool, again, there's a navigation device which sits in the car, and the next slides I have a video. It actually triggers the recording of the sensor bot, right? So the driver does not need to look into, do I need to record, do I not need to record? Why? Why would they? I mean, the tool knows everything, and the tool can kind of, you know, toggle the recording in the box, which makes it super convenient, right? And which, again, I mean, we try to solve all the problems that we could run into basically with software, right? So really, our drivers, I mean, their main task is to not think themselves, right? I mean, just follow the thing and just do what the device says, and then you'll be good, right? And it really helped, and it took a lot of time to actually get to that point, right? Okay, I can start with this video here. Again, this is again a navigation device. Here you can see it on the right. It sits in the car. It's a small computer, I guess, or something, right? And it triggers the recording of it. And this is basically what it looks like. This is some simulation, I guess, they did to test this. And it triggers the box recording, and it tells the driver actually where to drive and on which lane to drive. And this is kind of what has been previously on the, like I've shown on the previous slide, been optimized here. So this is an optimized round trip that tells the driver exactly what to do. And I mean, their task is to blindly follow that thing. I mean, don't get creative, right? Just do what the thing says. And that's how it typically works. Here's some live footage recorded from a video. That's basically what it looks like, right? So it has some audio feedback. It really tells the driver what to do exactly, and all the driver needs to do is basically drive. We attached some push buttons here to the steering wheel, which kind of tells the system on what lane the car is driving on. Yes, I know we could also detect this with cameras, but it's much easier to just put a push button on the steering wheel, and that's kind of the only task that the driver needs to perform. Okay. I'm skipping ahead a little bit here. So the driver is recording, and the driver has all the data on the box, and it's again stereo vision, LiDAR, GPS, and IMU. The data is compressed while we drive in the box because we have a small-scale computer inside the box. It's just a regular Linux computer. It's compressing the data. We kind of did some compression things ourselves. I mean, it's based on existing standards, but it's kind of doing it in a fancy fashion, I guess, right? I mean, biggest thing is to kind of compress 16-bit images. We want 16-bit images. It's important, we think, right? And it's a bit tricky, right? But my team built something that can kind of live compress the data in the box. It's just, you know, computationally wise, it's just at the edge of being able to do that, right? It's kind of lagging behind even a little bit, which is not an issue. But that's kind of how they tuned this to do, right? And then the data is copied from the box to our servers, and then we do a lot of stuff on the servers, right? And on the servers, we do basically two things. First thing is we need to compute what we call a reference trajectory, right? So we take the data from the cameras, we do the calibration, we take the GPS, we take the IMU, right? And what we do then is do large-scale bundle adjustment, right? I think this is, this audience, it's crystal clear to do it this way, right? But that's what we do. But here we kind of pack this into a product, which again is slightly different to doing, academic research, right? Here we did this on tens of thousands of kilometers, right? And we have customers in the end that either pay or don't pay if they're not happy, right? So it needs to work, right? There's no way around it. And that's kind of what we built here. And what we do is we use our stereo vision system. We track features. That's expected, I guess, right? Run large-scale bundle adjustment in a number of stages. And kind of what we build is a system that can kind of partition the entire huge graph, which is way too big for any computer to optimize jointly, kind of cut out smaller areas that can be computed, right? And then run several stages, one after the other, to consecutively grow these regions, and then ultimately in the end do some final optimization stage, which still tries to optimize regions which are as large as they can get, right? And we do use GPS along the way, right? Just so you know. I will let this video run here. It's a fairly long video here. Let me just maybe pause and explain a bit. So what you see here is you see these features that we track. And these are already the ones which our system detects as inliers. Obviously, we need to make kind of distinction between inliers and outliers to get rid of the noise, right? And we try to distribute these features evenly over the image plane and also spatially so that we get an even distribution of these feature tracks. And then we run fairly vanilla, at least in some stages, fairly vanilla bundle adjustment stuff. And then these arc-shaped white squares that you see here are basically poses, not every single one of them, but like every 10th or so pose of a camera projected into the image, which basically means you see the driving trajectory projected into the image here going forward, right? And maybe pause here, it's also quite interesting actually. Obviously we're taking the off-ramp here, and if you spot in the distance, you can actually see where that trajectory goes, right? So these are the arcs I just mentioned. We will take a left turn here, then coming back here, kind of going the other way around, and you can see where the trajectory is. And you can also spot from this, does it work at all, or is it grossly off? Even that question can be answered, I think, at least from this image, because it looks, it's not a final quality step, but you can tell it, at least eyeballing it, it fits nicely. And we do know that it fits perfect, or not perfectly, but very, very well, right? And you can always spot from the image here, right? Oops. Okay, let's just run a little bit. Again, we do some image processing, sometimes on 8 bits, sometimes on 16 bits. We try to keep as much contrast as we can. So this is an even out, contrast-wise evened out image for the purpose of showing it here at the conference. But most of the image processing happens kind of on a tone map version of that image, which has a number of benefits to do that, right? And here you can see, for one, you can see how the features are distributed, and second, you can also see what the trajectory is. Here again, if you look on the left-hand side, you see kind of where we came from, and it fits quite nicely, I think. You can also see how stable these features are. Stability is something which influences what feature tracks we use, because we have much more feature tracks than you see here, but there is a first heuristic that kind of makes selection of what feature tracks to use. Okay. Okay. What's under the hood? What's important in doing these things? Now, I said in the beginning, we drive on each lane once, and that is the case, right? And then you have situations like this one here, right? So you have a tunnel, right? It's in Japan, I guess, again, somewhere. No GPS, obviously, right? We've driven on each lane once, on the right lane, on the left-hand lane. In this tunnel here, we do all the bundle adjustment, visual navigation, we kind of called it, thing, large-scale slam, right? And it will still not fit perfectly in the tunnel. You cannot expect that. There will be drift that accumulates over these large areas where there's simply no GPS available. There's nothing you can do about this. No matter how good your slam is, it will always drift, right? to some degree, right? And here at this stage, we automatically assign features between these two different drives. So this is one, and this is second. So it's same location, one on the left, driven on the left lane, one on the right lane. And these features that you see here, these kanji signs, are automatically associated with the same features on the other drive, right? And their spatial position, was there a question? Okay, so their spatial relation in the other image stream, on the other trajectory, is actually here. So that's, let's say, 5 meters or something, right? So this single point, which should be at the same location, has been detected somewhere here in the other drive. So this is basically the drift. These, what color is that? Cyan colored lines tells you the drift in the middle of the tunnel after bundle adjustment, but before loop closure, right? And then we do the loop closure thing. We associate these image features automatically, doing some things, and re-optimize everything. And then in this step, we bring these two, in this case it's two left and right trajectories into, let's say, near perfect alignment, right? And that's pretty cool because that allows us to do stuff where there's no GPS. And it blends in nicely, right? I mean, if there's a tunnel, there's GPS before and after, but there's none in between. We have to do nothing. I mean, it's not that we special cases anywhere. It's just the optimizer, how it's set up, it just takes all the information that they can get and optimize it in such a way that it makes sense and that it kind of consistent, right? So it's a continuous thing no matter what, right? Even if we have global drift, which we still do after loop closure, it's still consistent locally, and that's key. I mean, that's much more important than anything else. And then we can also map underground garages. There are 2 levels in this very specific example. It's really just a benchmark. It's really just a test to see, can we actually do this? And yes, we can, doing this method. And you can see 2 layers of that parking garage, underground parking garage, overlaid over one another. So, and you can see how well that aligns. I mean, there are 2 levels. They're brought into almost perfect alignment here with this loop closure stuff. So it's a video for this. Karlsruhe again, test drive, driving into the garage. And then GPS gone, right? The optimizer and the adjuster just simply takes the streams from the imagery, also using the IMU, right? And then this is basically what it looks like. And yeah, I think it's quite nice actually. And it's really mostly coming from the vision part. I mean, the IMU that we use, it's a low-cost IMU. It's, I mean, not even worth to mention. It does help to robustify things, but it's not like it's kind of saving us along the way to get large distances or anything. It's really coming from the vision part. Okay, looks like I'm talking 30 minutes already, so I'm trying to come to an end here slowly. Couple more slides left. So first step is reference trajectories, right? We do this. And here you see parts of San Francisco. It's not exhaustive. It's not all of San Francisco. It's more financial district and the blocks that you see here. This is a coastline, actually. And after we do the loop closure thing and the visual navigation thing that I mentioned before, we are now in a stage where we can generate with our software very dense top views, orthophotos, right? And they look something like this, right? So this is this high-level view on the San Francisco side, but if you zoom in, it looks like this. So it's super high resolution. It's just below a centimeter per pixel, right? So it's sub-centimeter resolution. Doesn't mean accuracy, but resolution. And it's very helpful in doing things along the way, right? And it's generated automatically. Again, you will see no discontinuities here, right? No jumps, no nothing. I mean, take that road here. I mean, again, driven on each lane. The grayscale pixels here for the dashed patterns is coming from partially from the right lane drive and partially from the left lane drive. And it's just kind of 10 different parts for each single dash coming from the right and 10 other different parts coming from the left part. So it's really very small things kind of stitched together. And if we didn't have good loop closures, you would see some zigzag, right? Because the part coming from the right wouldn't fit the part on the left. Even if it's only a few centimeters, you would spot immediately, right? So even if you look at these images, it already kind of conveys a feeling for what is the local accuracy here, what's the local relative accuracy here, what's the consistency here, which directly relates to loop closures, right? more examples from Asia. Again, you can zoom in into these quite far and really pick out a lot of details from it. And it helps, right? I mean, it helps in building the maps then on top of this, right? Yeah, so that's basically all coming from vision. All we need to do this is two cameras and GPS, and then kind of extracting the features. I haven't even, explained anything about this. It's a step that comes after, right? So it's first reference trajectory, then doing these high resolution ortho photos, and then extracting features. No surprise here. I mean, I'm sure all of you guys are, know much better than I how to do this. Use state-of-the-art artificial intelligence. We compute a semantic segmentation. We have trained our nets specifically on our data. We are in a very comfortable position to do that because we can also build these maps at least with manual work, right? And that means we have tons and tons and tons and tons of training data, which is nice for a change, right? And so we not ever get any external labeled data. We have plenty of labeled data ourselves. It goes through some more scrutiny and some more cleanups, and then we can actually use that as training data quite easily. And then we do semantic segmentation. It's only the tip of the iceberg. I mean, it's far from any spatial features, but it's a nice springboard to kind of extract geometry and attributes and relationships from this. And this is a video. Everything you see in this video has been generated fully automatically. Okay, let me talk about this for a sec. So it's been generated fully automatically, and this map is not perfect. So we would never, ever in life deliver such a map to customers, just to be on the safe side, clear side here, right? This would afterwards go to heavy QC and quality control, checking by humans, right? Every glitch, almost every glitch, would be removed from the data set before we deliver, just to make that part clear. This is really for being at a very scientific conference to kind of give you a look behind the curtain. How good is automation? That question is a very vague question, very difficult to answer, but this is an example of what comes out of our automatically detected maps. Again, everything that you can see in color has 3D information of where that stuff is. Oh, let me go back. And that's kind of where we're at the moment. In urban environments, it's more difficult to do auto detection. For example, this one, I mean, there's rubbish, obviously, right, would be detected and spotted by humans and corrected. But things like these dash patterns, for example, that's kind of on the easy side for us because you've seen these top views. I mean, you can do things to kind of detect the lanes and then kind of marching along the lane boundary and kind of chopping this into the small pieces. I mean, I guess you can kind of picture how that works, right? It's very robust to do, and it's very nice to have, right? Okay. Finally, we clean up the mess that the AI produced. We are very lucky to have a very strong company in Ukraine that works with us. It's called Mindy Support. I mean, it's an extremely good team, very reliable, doing a fantastic job here. They are working with us, and we work with them for a number of years now. It's very fruitful cooperation, so I'm very happy to kind of announce this, right? And they help us to kind of spot any errors in the data and kind of clean out the glitches that we find here and there that the AI has produced, which does happen. I mean, it will never go away. It's just a question to how much mess do we need to clean up. And then in the end, it may look something like this. And then again, we have a polished and shiny 3D map that can be used, right? To wrap things up, let me show another video here. This is again Germany now, Ingolstadt. We can't name the customer, but it's in Ingolstadt. And yeah, it's a fairly exhaustive and complete map that we did here. Even the manhole cover has been mapped. I mean, I guess it's debatable whether that's needed or not, but it heavily depends on the use case. So there may even be use cases where that stuff is needed, and then we can do it, right? And we are approaching an intersection here. You can see all the paint on the road has been extracted. I mean, this is also, I mean, just there's no confusion about this, right? So this map is what it looks like after it has gone through quality control, right? So this is really after our Ukrainian colleagues have gotten their hands on this and kind of cleaned up a lot of stuff. And it's really what our product is in the end, right? So this is what, we make a living off, right? With these 3D maps. Okay. This is it. I will come to an end here. Thank you so much again for giving me the opportunity to talk to you guys here. And I suggest to open up for questions.
Yes, thank you very much for the great talk. Now we have time for questions. I think you already have a question.
Okay.
Is the microphone on?
Hello? Henning, can you hear me?
Yeah, now I can hear you.
Great. So once the map is created, it becomes old. If there's like traffic work or road construction going on, how would you update the map? If you drive with your mapping vehicle, it might be expensive to do that. But if you have a fleet from the customer vehicles, will that be a way to go to map the world in that area?
Yes. Yeah, that's you're asking the right questions. I mean, it's an excellent question, and maybe it's the single most important questions to get answered in the 3D mapping space. I mean, if you do get a 3D map, it's helpful to have, right? I think that's consensus. But the question is, okay, does it have a future, right? It's kind of what's in part of your question, right? And I mean, I'm convinced that the answer is clearly yes. It does have a future, and we can update the maps based on fleet data, right? I mean, especially now that we are part of the Bosch company group, right? I mean, there are other activities within Bosch that look into mapping. They do have access to fleet data on a massive scale. I mean, we're talking thousands of kilometers per minute, right? And that can be merged and used for these kind of things as well, right? But then there are also two types of updates. One is a critical update. One is, let's say, a soft update, right? If there's a lane closure or something, then any automated vehicle will need to detect this on board anyway, right, in a safe manner. And that information can obviously be easily updated into the maps without redriving with a mapping vehicle, right? And if there are more severe updates needed, let's say there's an intersection which is rebuilt into a go-around, then we'll have to send a driver. And whether or not it's too expensive or not, I don't want to answer the question because it depends on the business case, right? I mean, it could be easily that it doesn't even matter, right? I mean, that you can simply send a driver. It's a matter of how expensive can it be, right? What's tolerable. And that's more a business question than a technical one, in my opinion.
Hello. I want to ask about the auto calibration. As I calibrate the left-right camera and also the MU using bundle adjustment. And how many frames do you need to do it?
Unfortunately, I couldn't quite hear what you said. Could you maybe on the microphone
the question is about the auto calibration. Okay. You take left and right cameras without knowing the intrinsic and extrinsic parameters. Am I right?
Okay, I heard something about collaborations. I'm not sure if that was a question. So
no.
I mean, we work with Bosch now, right? I mean, there's no other collaboration other than that, right? I don't know if that,
I can
that
also
was a
repeat the question, maybe to get rid of the confusion. So the question is regarding, he's assuming that you don't have access to the extrinsics and the intrinsics of the stereo camera pair. And the question is, like, how many frames do you need in bundle adjustment to optimize this jointly?
All right. Okay, maybe it was a calibration question, not collaboration. Sorry, I couldn't hear correctly. Yeah, we do calibrate. We do calibrate the entire sensor setup, right? We do know intrinsic camera parameters, including lens distortion and everything, and we do know extrinsic camera parameters, meaning the displacement between the cameras and the IMU and the GPS and even the LiDAR, right? And this is something we build that we can automatically calibrate with the data we have, right? So every time we get the data, we can calibrate these information. And it's key, it's key. I can really only say that, right? I mean, kind of doing it all the time and on the fly, the recalibration thing, it really is kind of important to get to the kind of accuracy that we get, because as otherwise you would be bound by poor calibration to where you can get, right? And we recalibrate all the time automatically. It's running in the background, right? We don't have to do that manually. So we do know this information. And second question is how many frames we need to run the bundle adjuster. I mean, we record with 20 Hertz, so it's stereo with 20 Hertz. And when we are driving, we take all the data we get. And I mean, we bundle over many kilometers, right? So it's a lot of data, right? It's a lot of frames, right?
Okay, we have another question.
After that or something, do something like a bus or truck, you don't see lines on right of you.
Yeah, I can't hear a thing. You have to repeat the question. I
Okay,
guess.
maybe I can repeat the question very quick. So the question is going in the direction if you drive along the streets and probably you have a bus or a truck occluding parts of the street and you don't see the street lines, how do you know and what you do about it?
Yeah, also great question. We drive on each lane once, and that kind of solves the problem, right? I mean, we simply drive often, and that allows us to pick up everything. And I mean, you can construct some edge case where there is a parked truck constantly doing all the 3 runs, It doesn't happen, right? I mean, period, right? I mean, we drive on each lane, and that kind of solves the problem, and we don't have occlusion problems. Also, if you look at the top views, right, there are no signs of any other traffic participants, right? It always looks like there was no one. If you look at the top views, right, there's no shadows, no nothing. Obviously, that is not the case, right? I mean, it's crowded traffic, right? But since we drive on each lane, we can slice the data right in front of the car and kind of stitch that together, and that gives a complete picture without any occlusion.
Is there any? There's one more question from the audience. Yeah, maybe I can repeat.
Yeah, so you mentioned that you do some quality control after recording. And my question is that fully manual? So do they have to check every frame separately, or is there some automatism behind that?
Yeah, I could hear the question. Yes, I mean, QC is fully manual, right? We believe in the human in the loop, right? At least in level 4 maps. In level 2 maps is a different thing, but if you look at fully automated vehicles and the maps that's needed to do that, you need humans in the loop, period. It's only the question to what extent, right? It's not a 0-1 thing, it's really a continuous thing. How many humans do you need? How many effort, how many time, how many latency do you have? How much money does it cost, right? But yes, in the current status, every meter of every map for every feature will be checked manually, yes. We don't think in frames so much, but we think in more in route length or something, right? In map length. So every meter will be checked by a human, sometimes even repeatedly, right?
Okay, thanks a lot for the question. I may have a very follow-up question on that part. Since you're kind of heavily advocating humans in the loop, do you where do you see the future of HD mapping? If you would, let's say, eventually would like to map the whole world, and you also would like to keep it up to date, and you're saying humans are really needed in the loop, do you think this will kind of ever scale, or you believe in other solutions?
I mean, this is a bit of a crystal ball question, obviously, but I have a clear opinion on this. There are 2 major activities in the mapping space. One is the stuff that we do here. I mean, safety driven, and whatever it costs, it's just needed. Looking heavily at level 4 stuff, right? And you don't need to map the entire globe for level 4. I mean, that's a misbelief, right? It's not needed, right? You just need to map where you actually operate a viable business model with level 4 vehicles. And it's not going to be the entire planet, not even close, right? It's going to be from small regions to larger regions to highway networks to something else. But it's, in my opinion, very manageable for the next 5, 6, 7, 10 years maybe, right? Doing it the way we do, right? For level 2, partial automation is an entirely different thing. There it's heavily driven by coverage. The more, the better. It's more features, more updates, more coverage. That's what's driving this space, because you still have the human as a backup. I mean, safety is simply not as important and reliability as in the level 4 space. And these two major activities, be it within Bosch or be it outside of Bosch, will converge, right? I mean, the one will become more than the other, and the other will become more the same as the first approach, right? And these two will simply converge, right? And we kind of trying, and that's also what we work on, trying to combine the best of both worlds, right? Getting high update rates, getting high coverage, getting high safety along the way. And the question was about the humans in the loop. Again, in my opinion, it's not so much whether you do have any humans in the loop or if you have none. That's not the question. I don't want, I don't think it's relevant. It's more to what extent do you need the humans, right? And does your business case kind of cover the costs for it, right? And from that perspective, I think humans will remain in the loop for quite some time.
Okay, thanks a lot. I think that's a very wonderful concluding remark, and I think we can end the session here. And I would like to thank you again for giving this great talk.
Yeah, thank you guys. It was a pleasure to talk to you. Thanks so much.
Yes, thanks a lot for joining.